everyone, this is Papya Datta working as a lecturer in Devi Mahalakshmi Polytechnic College. Today I am going to start with the third bit of first chapter, that is channel capacity, Hartley's loop and Shannon-Hartley's theorem. So here we are going to discuss about the theorems used in Shannon-Hartley theorem, and we are going to solve some of the problems related to Shannon-Hartley theorem, channel capacity. Okay, so let's get started. First we'll understand what exactly a channel capacity is. Channel capacity is one of the most important parameters of a data communication system. Channel capacity represents the maximum rate at which data can be transferred between 2 points in the system with small probability of error. The upper cutoff frequency of the channel is approximately equal to the channel bandwidth. It is the bandwidth that determines the information capacity of the channel. The channel capacity expression becomes C equal to 2B log 2 of N. So here B is the bandwidth and N is the number of different encoding levels per time interval. Now if we use more than two levels or other symbols per time interval, then channel capacity in bits per second can be higher, and that time we can use the formula log 2 of n equal to log 10 of n upon log 10 of n for number of different levels. Now we'll talk about the Hartley's law. So in 1928, information therapist Ralph V.R. Hartley of Bell Labs published Transmission of Information, in which he proved that the total amount of information that can be transmitted is proportional to the frequency range transmitted and the time of the transmission. Shannon theorem states that given that a source M is the source, which is equally likely messages, like the same messages, equally likely means which contain same messages, with M greater than 1, which is generating information at a rate R and channel capacity C. Now, if this rate is greater than or equal to channel capacity C, then there exists a coding technique such that the output of the source may be transmitted over the channel with a probability of error in the received message, which may be made arbitrarily small. Now, this theorem is concerned with the rate of transmission of information R over a communication channel. The channel capacity C is a rate of transmission in bits per second. According to this theorem, for R less than or equal to C, transmission can be accomplished with coding without error in presence of noise. Shannon introduced the concept of channel capacity, the limit at which data can be transmitted through a medium. The errors in the transmission medium depend on the energy of the signal, the energy of the noise, and the bandwidth of the channel. So these three things are dependent on the error in the transmission medium. Conceptually, if the bandwidth is high, we can pump more data in the channel. See, if the bandwidth of any signal is high, then we can add as number data as we can. If the signal energy is high, the effect of noise is reduced. According to Shannon, the bandwidth of the channel and the signal energy and noise energy are related by the formula C equal to W log of 2 1 plus S by N. Here, where C is the channel capacity in bits per second, W is the bandwidth of the channel in hertz, S by N is the signal to noise power ratio. So this formula is used to solve various problems. So SNR generally is measured in dB using the formula Sn within bracket dB in terms of dB is given as 10 log of S by N, that is signal power by noise power. Now we'll take one example. For example, suppose that we want to transmit data at a rate of 10,000 bits per second over a channel having a bandwidth B equal to 3000 Hz. Now to transmit data at a rate of 10,000 bits per second, we need a channel with a capacity of at least 10,000 bits per second. Now if the channel capacity is less than the data rate, then errorless transmission is not possible. Okay, that time errorless transmission will not be possible. So with C equal to 10,000 bits per second, we can obtain S by N requirement of the channel as given by the formula S by N is equal to 2 raised to the C by W. C is the channel capacity and W is the width minus 1. So here your channel capacity is 10,000 bits per second and your bandwidth or width is 3000 hertz. Then 10,000 divided by 3000 will become 3.333, and if you calculate it you will get the value 9. Thus the bandwidth reduction from 10,000 hertz to 30,000 hertz results in an increase in signal power from 1 to 9. Now let's just take a minute and try to answer this question. On which factor or factors does the channel capacity depends in the communication system? The capacity relationship is given by which formula, and according to Shannon-Hartley theorem, which one is the correct statement? As all the answers are given, so here on which factors the channel capacity depends in the communication system, that is both bandwidth in SNR. The capacity relationship is given by C equal to W log of 2 1 plus S by N. The first option is correct, and according to Shannon-Hartley theorem, your channel capacity does not become infinite with infinite bandwidth, and it has a trade-off between bandwidth and signal to noise ratio. So both B and C options are correct. Now let's move forward and solve some of the problems. So first problem is one internet service provider, that ISP, gives dial-up connection at 56 kbps. Okay, assume that the telephone connection provides a usable bandwidth of 3.5 kHz. What is the minimum SNR required to support this? See here, your channel capacity is given as 56 kilobits per second, and your bandwidth, that is B or W, is given as 3.5 kilohertz. Instead of W you can also write down B. So here we have to find out the value SNR, that is S by N. I have to find it out. The formula for Shannon-Hartley theorem is C equal to W log of 2 1 plus S by N. We know the value of C, we know the value of W. So we will put the value of S by N, that is given as 2 raised to the C by W minus 1. So here value of C is 56 and value of W is, or B is, 3.5. Then if you calculate it, it will give you 65.535 SNR. So in terms of dV, if you calculate, it will give you 48.16 dV. Let's see another problem. Calculate the capacity of a standard 4 kHz telephone channel with a 32 dB signal to noise ratio. SNR is given, and your 4 kHz, that is your standard. See, the standard telephone channel occupies the frequency of 300 Hz to 3400 Hz. So if I do the subtraction, then I will get the bandwidth as 3100 Hz. So here SN is given, S by N is given. So the signal to noise ratio in decibel is 32 dB. So hence 10 log of 10 of S by N is given as 32 divided by 10. So you will get the value as 3.2. Then we take the log sign to the right hand side. We will take the anti-log. We will get the value 1584.89. Now capacity of the channel, we have to find it out. The formula is W log 2 of 1 plus S by N. So C equal to 3100, that is the channel bandwidth, bandwidth, into log 2 of 1 plus 1585. Then it will become 3100 into log 2 of 1586. Then log 10 of 1586 upon log 10 of 2, it will give you the value as 32953. So this is the channel capacity, which is in bits per second. Let's take last problem. We have a channel with a 1 megahertz bandwidth. The SNR for this channel is 63. What are the appropriate bit level and signal level? So here width is given as 1 megahertz, and your bandwidth is given as 1 megahertz, and SNR is given as 63. We have to calculate the value of C. So W log 2 of 1 plus S by N, it will give you, W is given to 1 megahertz. 1 megahertz means what? 10 raised to 6 hertz. So 10 raised to 6 log 2 of 1 plus 63, it will become 64. And if you calculate 10 6 log 2 of 64, you will get the value 6 megabits per second, which is the channel capacity. I hope you have understood the problems related to Shannon-Hartley's theorem and concept related to channel capacity and Hartley's law. Thank you.